Right, ladies and gentlemen, welcome to the linear algebra course. We will be dealing in section 1.1 with systems of linear equations, specifically the introduction to system of linear equations. So I believe that you would have probably already seen some of the concepts that we are going to discuss in section 1.1. So the first concept is that of a linear equation. Now, a linear equation in two dimensions has this particular form, where x and y are the variables and a and b are the coefficients. And in three dimensions, if we extend it to three dimensions, our linear equation looks like that. So we've got three variables, x, y, and z. And we've got the coefficients that correspond to the variables, namely a, b, and c. So the generalized form of a linear equations of n variables will be denoted in that form, where a1 up until an are your coefficients. If this value b that we have there, if that happens to be 0, we call the linear equation a homogeneous linear equation. Okay, and so a linear homogeneous linear equation has this particular form. So homogeneous linear equation is a special type of linear equation, and we're going to see later on homogeneous system of equations. They've got special properties and they're quite important. Right, so this example here, they ask us to basically apply the definition of a linear equation. So we need to establish which of those equations are linear and which are not. So we just need to look at the form that an equation has to be in for it to be called linear. Okay, so let's look at the first equation. So let's look at the form of, recall the form of a linear equation. So each variable is a standalone variable within itself, and so you can easily see that that is a linear equation. Each variable is a standalone variable. All right. Okay, so equation 1 is a linear equation. The second equation, obviously, that's not a linear equation, okay, because that combination, the xy combination, causes a problem. So that is clearly not linear. Then that equation there is linear because we don't have any. We don't have a situation like in the previous equation where we have a combination of variables x and y. So that clearly satisfies the form of that equation needs to be linear. Right, then if we look at the second batch again, the first one is not a linear equation because that the variable x is not a standalone variable. It is within the sine function. So that's not a linear equation. This equation is also not linear because the variable x is not a standalone variable. It is within the function f of x equals x squared. And then lastly, the last equation is clearly a linear equation because it satisfies the form, the generalized form that we have there. Now, if you have, we refer to a system of linear equations or linear system as a finite collection of linear equations. So this is an example of a linear system because it is a finite collection of linear equations. In fact, it's a collection of 3 linear equations. The variables x, y, z, and w, they are called unknowns. So if we just go and generalize that idea and write it down in general notation, this system here, that is a linear system with m equations and n unknowns. So the index n counts the number of variables in that case, and the index m counts the number of equations. And obviously the x's denote they are my unknowns. And we say that a solution of this linear system in n unknowns is a sequence of numbers, S1 up until Sn, because there are n unknowns, so each variable should have a solution. These S's are the sequence of numbers is a solution. If and only if I plug them into the original system, each equation is satisfied. Okay, so after substitution, if I do the substitution there, I said x1 equals s1, x2 equals s2, and so on and so forth until I set the last variable equal to Sn. It will satisfy every single one of the linear equations in that list. Then we say that that sequence of numbers is a solution to that system. Okay. Right, so in the case of n dimensions, in other words, you've got n variables, the solution, we can write that as an n tuple. So it is a point with n components. So obviously in the two-dimensional case, we refer to them as an ordered pair, and in the three-dimensional case, we call it an ordered triple. Okay, just for you to take note of those definitions. We say that a linear system is consistent if it has at least one solution, and we say that it is inconsistent if there are no solutions to the system. Right, linear systems with 2 and 3 unknowns. Okay, now a linear system in 2 unknowns arise in connection with intersection of lines. If you go back to the first slide, recall that this equation is the standard equation for a straight line in 2 dimensions. So when 2 unknowns are at play, you can interpret it geometrically as a straight line. Okay, so if you have a system of linear equations and 2 unknowns, and if the lines are parallel to one another, and they are distinct, then this particular system in question will have no solution because there will be no intersection. Right, so if you've got those straight lines there, and each equation in the linear system is a equation with 2 unknowns, and remember you can represent it with a straight line. And if these are all, if the straight lines that these equations represent are all parallel and they are distinct, then they're not going to have any intersection, and so there's going to be no solution to this system. Okay, so in that case, there I've got a system of 3 equations with 2 unknowns. And the lines that they represent look like that diagram that I've drawn there. You can clearly see there's no intersection. Right. Also take note, if you could also have this type of configuration where you've got 3 lines or 3 equations in 2 unknowns, each one representing a straight line. And you could also have a situation where previously we had the 3 parallel lines, but you could always also have a situation where 2 of the lines are parallel, and one other line cuts the other 2 parallel lines. And in that case, you also don't have any solution, because these 2 points, for a point to satisfy the linear system of 3 equations, that point needs to lie on all 3 of the lines. And you guys can see these 2 points, they only lie on 2 lines as opposed to needing to lie on all 3 lines. So in that case as well, there we've got 3 equations and 2 unknowns, which is clearly inconsistent as well, because there are no solutions to any configuration of that form. Again, you could also have a situation where 2 of the lines coincide like that, and they are parallel to the other black line. And in that case, again, your linear system also is going to be also inconsistent, because although you've got points that lie on 2 of the lines, the points don't lie on all 3 lines, which is necessary for a point to be a solution to that particular linear system. Now, again, if you've got 3 lines, and these lines intersect only at one point, then obviously there's only one solution in that case, which is the point that lies on all 3 of the lines. Okay, so that happens if the lines intersect at only one point. Okay, now if the lines coincide, infinitely many points of intersection will mean infinitely many solutions. So there you've got your 3 lines and they coincide. So basically you can interpret them as basically being the same line, and so they coincide. So there we've got infinitely many solutions, because there are infinitely many points that lie on all 3 of those lines. So we're gonna get infinitely many solutions. Okay. Right. So in general, every system of linear equations you'll see that it either has a 0 or 1 or infinitely many solutions. Okay, you cannot find any other possibilities. So that makes linear systems nice in the sense that we only have one of the 3 possibilities. Either it has no solutions, or it is inconsistent, or it has exactly one solution, or it's got infinitely many solutions. All right, just quickly as an illustration in the case of 3 dimensions. So let's take 3 equations with 3 unknowns. Now we know an equation with 3 unknowns can be represented in R3 space as a plane. So I've drawn a black and a red section of a plane. And let's just illustrate this quickly. So let's take 3 planes, and right, let's take a linear system where the first 2 planes, they basically intersect in that straight line there. Okay, and I'm drawing the line of intersection there. Okay, and then we've got the third plane has the intersection in that line there. Right, and in that case, the 3 planes intersect in this indicated black line here, and in that case, we say the linear system has got infinitely many solutions, because any point that lies on that black line, it will lie on all three of the planes. So that's an example of a linear system with three unknowns and three equations that's got infinitely many solutions. Okay, let's look at another example. If you look at if you look at this plane here, it intersects that plane there. Okay, and I'm going to draw the line of intersection. Okay, there's the line of intersection, and then the red plane. Okay, the red plane, let's say it goes like that, and the red plane is parallel to the other black one. And I'm drawing the line of intersection, which is that line there. And these two planes are parallel to one another. Okay, and also these two lines again are parallel to one another. So in that case, we've got a system of three equations, three unknowns, and there is no solution to that system. That system is inconsistent, because the points on the black lines, they are the points that in question, and unfortunately those points only lie on two planes at a time. They need to lie on all three planes. Right, so let's just look again at one last type configuration. Again, we've got the three equations and three unknowns. And all three of them are planes in R3. So let's look at the case where the two black planes, they intersect basically in that line there. So again, drawing that intersection line, there we get the intersection line. And then we've got the red plane, which will run like that. Okay, and so basically the intersection line there is going to be that line. And that line there. Okay, so the right. So in that case, one can easily see that there's only one point of intersection, and it's that point there. All the other points lie only on two planes at a time. Okay, so in that case, that's an example of a linear system with three equations, three unknowns, such that we've got exactly one solution. So again, in general, a linear system either has one solution, infinitely many solutions, or no solution. Right, okay, so here we asked to solve the following linear systems. You guys should be familiar with that. We can add the first equation to the second equation, and we end up with 3x on the left hand side. The y's cancel, and that's going to equal to 12 on the right hand side, which is going to imply that x is equal to 4. Okay, and substituting it back into the first equation, we get that 4 plus y needs to be equal to 1, which implies that y is equal to -3. Okay, so that system has got exactly one solution. So you can see it as two straight lines intersecting in one point. Right, the second set corresponds to this linear system as the straight line 2x plus y equals 4. And the second straight line can be written as 2x plus y equals to 2. So this system corresponds to two straight lines that are parallel, and they don't intersect. So there's no solution here. It's inconsistent. It's two parallel straight lines. Okay. The third system corresponds to two straight lines. 3x plus y equals 1. And the second equation you can write as minus 3x plus y is equal to 1. So that's a linear system with two parallel lines that coincide. And so there are infinitely many solutions. Infinitely many solutions. Right, just by inspection. Right, the last system corresponds to the equations x minus y plus 2z equals 1. The second one, you can write it as x minus y plus 2z equals 1. And the last one you can write as x minus y plus 2z equals 1. Alright, so that corresponds, or that's equivalent to a system of three equations, three unknowns. And each equation signifies a plane in R3. So this is a linear system that corresponds to three planes that coincide. So there, looking at our example there's the plane. So we've got three planes, okay, and these three planes they coincide, okay. So the first plane is the same as the second plane, so I'm placing them on top of one another. And the third plane is the same as the other two planes. So these planes all coincide, okay. So again, this is a system that's basically got infinitely many solutions. Right, so next we've got, we are going to take linear systems and we're going to convert them into matrix notation, and then we're going to manipulate the matrix to find the solution. So that brings us to augmented matrices and elementary row operations. So again, here you've got a linear system as we described, and the augmented matrix of this linear system is simply the matrix formed by taking these entries here, making that the last column of my matrix, and then taking all those entries and aligning them to form the first column of my matrix. Then you can take all those entries there, and you can align them to make your second column, and then you go on to the last coefficient corresponding to the nth variable, and that is going to be your second last column of your matrix. So that is known as this is known as the augmented matrix. So just as an example here you've got the linear system, three equations, three unknowns. So that part there is my final column there, and 1, 2, 3, which is that section there. That forms my first column. 1, 4, 6, which is that part there. That forms my second column. And those coefficients there, that forms my second last column. Alright, so that's what the augmented matrix is as it relates to a linear system. That augmented, if we look at a matrix in general, we have three types of row operations that we can perform. We can either multiply a row with a constant, or we can interchange two rows, and that's the notation we use to interchange two rows, or we can change a row, the ith row, by adding a multiple of the jth row to it, which is denoted by that. And we always, in the third case, we always list the row that we change. We list it first. So in that case, we're changing the ith row by adding a multiple of the jth row to it. All right, so that is just what adds what I said there in the last case. Here's just an example. In the first case, we take this matrix, the first matrix, and we interchange the first and the second row. So there we take it and we interchange the first and the second row. And so we get this part here. Okay. The second case, we change the first row by multiplying the first row with 2. So we take this row here and we multiply it by 2 there. Okay. The third case is we add a multiple of one row to another. So we're changing the first row by adding the second row to it. So there we get the first row that's changed. All the other two rows still remain the same. And then the last one is we change the second row by adding negative to the first row. So we change the second row by taking negative to the first row and adding it to it. So there we get the change. So having said all of that, let's look at the following three examples just very quickly. The first one is, there they ask us, give an example of a nonlinear system with two solutions. Alright, so this linear system, x squared plus y is equal to 2 and y is equal to 1. You can go and solve this linear system, and from 2, we can substitute 2 into 1, and we can get the equation x plus 1 equals 2. And from there we can solve for x squared as 1, which implies that x is 1 or x is minus 1. Okay, so the solution space is pretty much, it's the point 1, 1, or the point minus 1, 1. So this linear, well, this system, it's not linear, it's a nonlinear system. It's got exactly two solutions. Okay, so there's my example. Then the second example, is that linear system consistent or not? So if we look at this linear system, is it consistent or not? And the answer is obviously, well, by inspection, yes. Basically, x equals y equals z equals to 0 is clearly a solution. Okay, so clearly if we make x, y, and z 0, the left-hand side in both equations is equal to the right-hand side. So that's clearly a solution. Then the last one, there they say the following is not an elementary row operation. So why is this not an elementary row operation? 2 times the third row minus 4 times the first row. So if we go back here, remember these are the only only elementary row operations. So in each instance, I'm only, in the first case, I'm only doing one operation at a time. In the second case, I'm just doing one operation. And in the third case, I'm just doing one operation. Because in each instance, I'm changing exactly one row. But we go back here, that is not a linear operation because I'm performing two operations in one. I am multiplying the third row with 2, and then I'm adding negative for the first row. So that's clearly not an elementary row operation. So we can basically convert that into a sequence of elementary row operations. And the sequence in this case will be, we will first take the, we'll take this matrix, and that particular row, we will change the third row first. So we'll change the third row first by performing this operation to the third row of the matrix. And we will then get a matrix with a new third row. And let's call that the matrix where the third row, let's call the third row of this matrix R3 prime. And then what we will do then is we will follow this up with another operation. We will change the third row of this new matrix, call it R3 prime. We will add that. We'll change the third row of this new matrix by adding a minus 4 times the first row of the original matrix. Okay, so there I've converted this this operation into a sequence of 2 elementary row operations, and the sequence in this case is the elementary row operation that takes the first matrix, the third row of the first matrix, changing it to twice the third row of the original matrix, and then taking that subsequent matrix that I get from that operation, and I just apply this third type of elementary row operation to it.